All right, so this is asymptotic notation, lecture 1. This is big O stuff, right? You've heard of big O of n and big O of 1 and so on. That's what this is. There's a little dark secret in software engineering, I think, which is that not a lot of people that you work with often know what the hell they're doing with asymptotic notation. The secret is that, you can just kind of get a hold of the intuition, and you don't need to know the mathematical underpinnings. So if mathematics is not your strong suit, I wouldn't panic at first. You can develop the intuition and sort of develop the rules, the operational calculus of asymptotic notation in your mind, and work off that instead. That's what almost everyone does, I think. Even people who do know the mathematical underpinnings. You just sort of develop the intuitive understanding and work off that instead. It's like a game. It has certain rules, and you just need to know the rules. So let's get into it. The whole point of asymptotic notation, asymptotic analysis, is to compare the long-run behavior of functions. So we don't care what happens for small values. If we're evaluating a function at 1 or 5 or 100, we don't really care. For asymptotics, we are specifically interested in what happens in the long run, in the limit, I guess you could say, way out there, in the long run. So if in this very particular mathematical sense, a function g of x dominates another function f of x in the long run, we say that f of x equals big O of g of x. It's a little bit strange, this notation. We use the equals sign, and we use the big O as a function, but what this is really, it's just really just notation. We're saying f of x is dominated by g of x, and we're going to be using those names, g of x and f of x, to indicate g of x is the one that dominates. It's a greater letter, so it has greater values. And by dominates, I mean the function's values are greater than the function's values of f. Okay, so g dominates means that f of x is big O of g of x. All right, that's pretty straightforward so far, but let's get into the mathematical definition. I can just read the notation here. F of x is big O of g of x if and only if, that's how you read this, there exists some number b in some x sub k such that for all x greater than x sub k, b times g of x is greater than f of x. So what does that mean in plain English? F of x is big O of g of x if and only if there's some point x sub k, you can see on the chart here, the plot, there's some point x sub k beyond which the blue function g of x dominates the orange function f of x. With the one little caveat that you're allowed to scale g of x by some constant factor b. So we can always scale our dominating function, g of x, by some constant factor. We can multiply it by 5 or 10. We can just pick one. It has to be finite, but we can pick one and scale it and see if that still holds in the long run. And it will in this case. The blue function, g of x, is a parabola, and f of x is a straight line. And we know that eventually, no matter what the constants you use in your parabola are, as long as they're positive, a parabola will eventually outpace a straight line. And we can make our parabola steeper by multiplying it by a constant, b in this case, but we don't have to. So the b is a little bit superfluous in this example, but we'll see another example where it makes sense. So this is the basic idea. There's some crossover point where beyond that point, at least, beyond x sub k, the blue function g of x dominates f of x. Subject to the proviso that we can multiply g of x by a constant factor. Okay? So our first rule, our first little a rule of the game that we can develop some intuition for, is that constant factors on our functions don't matter because we're allowed to tweak this b, right? So f of x is 10x, and g of x is just x in this example. Is 10x big O of x? You think, well, 10x isn't dominated by x, but it's still big O of x because we can choose our b. If we go back to this mathematical definition, there's some b such that this domination relation holds. We can just multiply our g of x by some b. As long as there exists some b that makes that true, then we're good. We're golden. And the equals big O notation still holds. All right? So in this case, our x sub k is 0 because we don't need to pick some crossover point. We can just start in the beginning. And the blue line always dominates the orange line if we just pick a b that's greater than 10. In this case, we picked 11. And we can see that g of x dominates f of x. So f of x is big O of g of x with this b that we've chosen of 11, which is fine. We can pick whatever we want. We would say colloquially that this is linear in x, or order x. We usually, you can say big O of x, but often people will mix in other terminology like linear in x or order x. Okay. That's our first rule. Our second rule, constant offsets don't matter either. We can just add a constant to our function. It doesn't change anything at all. Here we have two different functions. G of x is x squared. It's 2x squared. And the orange line is x squared plus 5. We've chosen b equals 2. And we can see that even though we've shifted the orange function up by 5, we can shift it up as much as we want. It doesn't fucking matter. Like, we're always going to be able to overtake it eventually by just outrunning it in the long run. 2x squared is going to dominate x squared plus anything in the long run. Just the behavior of parabolas, or mathematical functions in general, actually. So we can just choose our multiplicative factor to overcome any constant additive factor that we want to add. All right, so this is our second rule. Constant factors don't matter. You can just ignore them when you're doing asymptotic analysis. You can ignore constant factors and constant offsets is what I meant from this slide. So the question, is x squared plus 5 our orange function, big O of x squared? Yes. Again, maybe counterintuitive if you just look at it like, oh, wait a second, how is x squared dominated by, how does x squared dominate x squared plus 5? But it's because we can choose b equals 2. And you can see it in the plot, 2x squared outpaces the orange function x squared plus 5. The crossover point is x sub k equals square root of 5. If you're curious, it doesn't really matter. You just get that by solving the function, set them equal to each other, solving the equation. So, since x squared plus 5 is big O of x squared, we say that it is quadratic in x, or order x squared. All right, those are our first two rules. Third rule of life, we can always ignore lower order terms. So, is x squared plus x big O of x squared? The answer is yes, we can ignore this lower order term, this plus x, it doesn't matter. Because if we just scale the higher order term with our b, our magic like slider on b, we can choose b to be whatever we want. We can just scale the g of x function, which will scale the higher order term in a polynomial. It'll also scale the lower order terms, but they don't matter. And there's only one term in this case anyway. We're scaling the higher order term, and that will dominate the other polynomial because the higher order terms are the same. Yeah, you just pick like b equals 2 or b equals 1.1 or something, and you'll see in the plot that the blue function x squared can overtake x squared plus x if you just scale the blue function by some b, which is 2 in this case. So we would say that x squared plus x is big O of x squared, or quadratic in x, or order x squared again. This is our third rule. We can ignore lower order terms in a polynomial. So just look at the highest order term. X squared is big O of x cubed. X squared plus x is big O of x squared. We just cut off all the lower order terms and look at the highest order term, and that's all we care about. Again, like the mathematics, even if the charts and plots, whatever, are kind of escaping a little bit, which is, it's fair, then just, you can remember the rules. I'll have a summary slide too, so you can look at them all over. But we have another rule on our plate, is logs. So we might have logs of different bases if we're comparing f of x and g of x. Here f of x is log base 10 of x, and g of x is log base 2 of x. In computer science, we often like to abbreviate log base 2 as just lg. It's very convenient. The mathematicians like to abbreviate natural log base e as ln, so we get one too. We get lg for log base 2. Is log base 10 of x equal to big O of log x? Yes. And the reason is just arithmetic. You can do the change of base formula. This is a kind of alternate form of it, but it still works. Log base 10 of x is always equal to log of x times log base 10 of 2. And we've used this alternate form so that we can get it into this familiar form where this is just a constant. This is just b. And we know from our first rule that we can ignore constant factors. So we just lop this off and say that log base 10 of x is big O of log of x. Or we say order log x. Here in the plot I have shown that you can make them overlap exactly by choosing b correctly. In this case, b is chosen to be log base 10 of 2, and this is just sort of the constant factor that we have in the log base change of base formula. And so we just add some epsilon to it in order to beat g of x. Yeah. And if you're not familiar with logs, this is important. You need to know what a log is in order to express yourself in asymptotic notation and talk about it intelligently. A log, this is the definition of a log. If a equals 2 to the c power, then that's the same as saying c is log base a. So c is the number of doublings required to get from 1 up to a. That's what the log represents. That's what it expresses. So if you need to double yourself 4 times to get to 16, then log base 2 of 16 is 4. We've done 4 doublings. The log base 2 of 1024 is 10. 10 doublings to get to 1024. And you learn these powers by heart eventually. Excuse me. Okay. So that's logs. That's our last rule, I think. No, there's one more. It's exponentials. Exponentials kick the ass of polynomials. So here we have f of x is 2 to the x plus 1, and g of x is x to the 10th power. Now, is 2 to the x plus 1 big O of x to the 10th? I mean, this is a 10 in the exponent. That's pretty big, right? X to the 10th power grows fast. It goes real fast. But 2 to the x in the exponent, instead of x in the base, grows even faster, eventually. And that's just a rule. I mean, it's kind of intuitive, right? Exponential growth is like synonymous with things growing fast. And you sort of intuitively understand, too, that successive doublings grows very fast. So you can see the long-term behavior around like 59 or so. The functions cross each other at 6 times 10 to the 17th. And eventually the orange function, the 2 to the x plus 1, does dominate. Of course, the plus 1 doesn't matter. We know from one of our rules we can ignore lower order terms, which is, well, we also have a special rule for constant offsets, but really that's just a special case of a lower order term in a polynomial, because it's x to the 0 power. All right, so in this case, we would say that 2x plus 1 is big O of 2 to the x, or it's exponential in x, or order 2 to the x. That is our last rule. So let's go over them all. Constant factors don't matter. Constant offsets don't matter, which is a special case of lower order terms don't matter. Log bases don't matter. You can assume they're all log base too, because you can always do a change of base formula and it's just multiplying by a constant factor, which we know doesn't matter. By the way, that's kind of an interesting fact, right? The number of multiplications by 10 it takes to reach a number, and the number of multiplications by 2 it takes to reach the same number only differs by a constant factor. Kind of cool. You might not realize that intuitively. Anyway, the last rule is exponentials dominate polynomials. All right, and here's some common big O's that you'll see around. Big O of 1 is constant time. Big O of log n is slightly worse. This is log time. Big O of n is slightly worse than that. It's linear time. Big O of n log n is worse than that. But it's still a really good running time for a lot of algorithms. If you can get to n log n a lot of the time, you're happy. Big O of n squared, you start going, can I do better than this? That's quadratic. And cubed, there are some like all pair shortest path problems and graphs and things like that that are n cubed that you can't really get around. But it's not great. You want to keep your n small in that case, if you can. Exponential time, ooh, you are doomed. 2 to the n, 3 to the n, or God forbid, n factorial. This is like solving the traveling salesman problem, if you've ever heard of that. It's really hard. You have to use approximation algorithms when n gets too large because you can easily run out of time left in the universe before heat death trying to run your algorithm if n is sufficiently large with a n factorial algorithm. We call this subset constant time all the way up to n cubed, including the logs. We call those polynomial time. And then everything 2 to the n, 3 to the n, up to n factorial is exponential time. Or, even worse than n factorial, like, n, 2 to the n times n factorial. Although in that case, it would still be n factorial. You know what I mean. N to the nth power, let's say that. That's worse than n factorial. There's some other funky stuff in between. Sub-exponentials, but you don't ever need to know that unless you're a specialist in algorithm development, like at a university probably, or in like a research department of a big company. All right. So far, we've only cared whether function g dominates function f, but it's often useful to bound on both sides, above and below. And this is what big theta does instead of big O. So you can see some examples. 2x squared is not big theta of x. 2x squared is not big theta of x cubed, but it is big theta of x squared. So it is, it's bounded both above and below. If you've heard of little o, which bounds on below, theta is just defined as big O and little o. So you just get balancing on both sides. So, even, if you wrote a big O here instead of a big theta, it would be true. No one would probably often write that. Usually when you just say, you just bound it as close as you can and get that result, because it's really a guarantee. Like big O is saying, whatever this function is, it's going to be less than what's inside the big O. So you want to keep that as tight as you can, just to get the best guarantee possible. So a lot of the time people will do that, and they could just write big theta, but almost no one does that. It's kind of a nerd thing. No one writes big theta, even though they are technically doing the same thing. Alternate notation, sometimes, very rarely, you'll see this little wavy equal sign to say that f of x is asymptotically equivalent to g of x. Okay, That's big theta. You can probably just say big O, it's fine. Yeah, what does any of this have to do with code? We developed some intuition, some like 5 rules of like how can we determine whether one function dominates another function. But what does this have to do with programming? Well, we can characterize running costs or running time or memory usage or network requests or file I/O or messages sent between actors or messages sent across the network. Who knows? As a function of the problem size. And this is the key. We have to determine like the problem size that we care about and then characterize the costs in terms of that running size. And once we do that, we can use asymptotic analysis to compare 2 algorithms based on their running cost to see which one will be more efficient for sufficiently large problems. Our n is going to be growing, n is our size of our problem. So we only care about sufficiently large problems. Okay? So what is f of x? Our function, our objective function we're trying to characterize is basically just the cost that we're trying to measure expressed in terms of some x. So if we're trying to sort an array, we have array sorting algorithms. Our x is going to be the size of the array, like how big is the thing we're trying to sort. And our f of x is going to be the number of comparisons. This is for a comparison-based sort. Like, how many times do you have to compare one element to another in order to get this thing sorted? That will be our f of x. And typical running times for sorting algorithms are n log n is the theoretical best you can do for a comparison-based sort. You can prove that. The worst sorting algorithms, I guess you could say, are n squared. There are very bad sorting algorithms like BOGO sort, which are n factorial, but those are a meme. Anyway, you do actually sometimes use n squared sorting algorithms, by the way. You wouldn't think like, oh, an n log n sorting algorithm based on our chart that we saw before, and based on just, putting it in a calculator and seeing how it grows, you would think is way better than n squared. But we'll see that there's some caveats there. If you're trying to multiply 2 numbers, x will be, like the size of your problem is going to be the number of bits required to represent the input. Not the number itself. We typically just use the number of bits. Otherwise, you have an extra, an extra 2 to the n in your asymptotic notation all the time. So just conventionally, you represent x as the number of bits. And you are operating on like 1 bit at a time, so or 1 byte at a time, whatever your atomic unit is. So it makes sense to use x as your problem size, number of bits. The f of x is the number of operations required to get the final answer. Number multiplication, the sort of elementary school algorithm, long multiplication, is big O of x squared. X is the number of bits or digits. Well, no, it's the number. Yeah, the number of bits or digits is the same because of our log base doesn't matter rule. You can do better than x squared, but not a whole lot better. You can get the constant factor down, I think. I might be wrong about that. There might be significantly better multiplication algorithms that use like fast Fourier transforms and stuff. Going on to graph algorithms. These are often multivariate, so you don't have just one x. Like you would have n as the node count or the vertex count, and m is the edge count. So your big O notations will look like, oh, this algorithm is big O of m times n, or it is m log n, something like that. And that's just like the number of operations characterized in terms of the input size, which is just 2 variables in this case instead of 1. Okay. But beware. Constants can be large in practice. This is a killer. I mean, we're talking about asymptotic analysis here, where functions behave in a certain way out, past some x sub k, which is potentially extremely large. It may be absurdly gigantic. There's a class of algorithms called galactic algorithms, which are known to be very good asymptotically. They're often theoretically the best algorithm known, but they don't pay off until very, very large problem sizes. Here's an example algorithm. This is Prim's algorithm, which is a greedy algorithm for finding a minimum spanning tree in a graph. Basically, you just have some nodes. You can think of these as like electrical substations, and like here's your electrical network, all the edges, and we've highlighted just the edges that you actually need. And we've minimized this like subgraph, this spanning tree across all the substations, so that we can get rid of all the other ones that are longer edges and sort of minimize our operating costs for like, how much does it cost to operate this network? We don't need all these redundant edges, right? We want the shortest ones possible. And that's the minimum spanning tree. Prim's algorithm is very good, and you use it in practice, of course. It's efficient. And in order to beat it, you have to resort to galactic algorithms, pretty much. There's some other ones with the same running time, Kruskal's algorithm or whatever, but if you want to get the asymptotic performance down below Prim's algorithm's big O, then you have to go to these absurd galactic algorithms. There's one that is like the best known algorithm, or the best algorithm with a known running time. Some of them have unknown running times because they're like randomized, and you have to do complicated amortized analysis that is very theoretically intensive, that people don't have the theoretical results yet to even know how long it takes. But the one that is known, the one that has a running time that is known, that is the best, requires something like 10 to 100th power operations before you surpass Prim's algorithm, which is super simple. I mean, I just wrote this pseudocode here. You don't have to look at it, but like you can see how simple it is. In order to beat this, you have to resort to some crazy randomized algorithm that is so slow that the advantage is so slight and takes so long to pay off that you'd have to be past the death of the sun in order to ever see it beat Prim's algorithm. So constants can be large. You got to be aware. We're throwing away a lot of information when we're doing asymptotic performance analysis. We're just sort of throwing away all the lower order terms. We're throwing away constants. We're allowing one function to just scale arbitrarily, right? How wild is that? But it is sort of just a useful rule of thumb for characterizing algorithm performance. So we use it anyway. And it's theoretically very satisfying. Typically, algorithms that have the same, often algorithms that have the same asymptotic performance can be reduced to each other. And so there's like interesting theoretical results. There's a reason that we do all this nonsense. And also just in practical terms, the constants can be all over the place. Who knows what, one machine or another might implement one thing more efficiently than another. But if you know sort of the shape of the running time, that's like, oh, this is big O of n log n, it gives you a good idea that this is going to be better than an algorithm that is big O of n squared. And you can just sort of talk in these general terms that are useful in practice, even though they're not very precise. You just got to have that little asterisk on the end of some of these algorithms saying, do not use this algorithm, because even though it's theoretically optimal, you're not going to see it pay off unless your n is extremely large. Or in the mathematical notation, the x sub k crossover point is going to be so far into like large n's that it'll never pay off. All right. Here's an exercise. Linear search. We're just doing a search through an array. This should be very easy to understand code. It's JavaScript. We're searching through an array for a value. We just loop through all the cur values of the array, putting it in the variable cur. and checking. If char equals the value that we're looking for, we return true. And if we get through the entire loop without seeing, the value we're looking for, then we return false. This is linear search. So how many comparisons does this take in big O notation as a function of the array length? That will be our n. I've been using x so far, by the way, to indicate the problem size, but that's just to emphasize the mathematical nature of this. Like, we are actually comparing arbitrary mathematical functions, but in computer science it's conventional to use n as the problem size. So our n is the array length. So how many comparisons does this take on average? Well, we're going through the entire array, potentially. Even if it's in the array, even if the value we're looking for is in the array, I mean, worst case, it's not in the array at all, and we have to look through all n, so that'd be, n comparisons. But even if it is in the array, on average, I mean, if our value that we're looking for is, its location in the array is randomly distributed uniformly, then we would expect that we'd get through about half of the array before we find the value. That's just statistics, or probability. So you can say that the running time of this is like half of the array, which is, we know from our first rule, that we can ignore constant factors, is big O of n. And this is a pattern that you'll see, in code commonly. You just have a for loop that loops over the whole array and does something. Then that is big O of n. We have n items in our array, we're looping them over them all, or at least, some constant factor of them, in this case about half of them. That's big O of n. That's like sort of a piece of intuition you can have. Here's another exercise. This is selection sort. It's a sorting algorithm that basically keeps track of a subset of the list that has already been sorted, and then we grow the subset of the list by one, basically by finding the exact element that's going to go next to it. So we just sort some subset of the list, like the lowest k elements of the list, and then for the k plus 1th element, we find the lowest element in the remainder of the list and stick it there. And we find the lowest element in the remainder of the list and stick it there. The lowest element in the remainder of that list and stick it there. We just repeat this. And this is a sorting algorithm. It will work. It will sort numbers, or anything that can be compared with each other. And we want to know, what is the asymptotic running time of this algorithm as a function of the array length? Our n is going to be the array length, which is conventional for sorting algorithm. Well, let's just ignore the code. Like, just blot this out of your mind. I mean, you can just see, just by glancing at this, that this is just a constant number of operations. It's just 3 lines of code that just 1, 2, 3. This is a constant number of operations. So we just consider this as a constant. Here inside the for loop, this is a constant number of operations. This is just one operation, so it's a constant. The thing we could really care about is these loops. Like, we have a loop that is going from 0 up to the array length, -1, but minus 1's fine, whatever. But it also is looping 0 to array length -1 is a total of array.length items, so 0 indexing fun. So we have array.length. We have n times through this outer loop, and on the inner loop we have again, the candidate index is going from the smallest so far, which will move along through the array as we go, but on average it'll be about halfway through the array because we're going from one to the other. So on average it's expected to be in the middle, and that will run to the end of the array. So on the outside we have n, on the inside we have half n, and then on the inside of that we have a constant amount of work. So we can multiply them all together. N times half n times a constant. We can ignore the half because of our first rule, and we come up with n squared. This is an n squared sorting algorithm. Does multiplication make sense? Because that's really what's happening. We're doing n on the outside, and for each of those n, we're doing half n work on the inside. So that's just multiplication, right? For each one of n, we have half of n going in the other dimension, And the area of this rectangle is half of n squared, which is just beta of n squared. If you also want to consider this constant work on the inside to be, I mean, there has to be constant work on the inside for this to mean anything, otherwise it's not doing anything. But it's just constant amount of work, so you can think of like the rectangle having a depth of 1. And it's a cube and you're finding the volume in the cube. Just some little intuitive tricks to think about these things. All right, a selection sort. And I guess I'll continue in the next lecture with recursion. I hope that was useful for asymptotic notation. I know that was a whirlwind, but if you've seen some of it before, hopefully it wasn't too overwhelming. And it really is just the basics of what you need to know.